To fall from the moon is not to simply drop back down to Earth. It is to throw a fragile construct of metal and silicon into a localized manifestation of hell. When an object returns from lunar orbit, it hits the upper layers of our atmosphere at nearly 25,000 miles per hour. At those velocities, the air itself cannot get out of the way fast enough. It compresses, tearing apart molecular bonds, igniting into an enveloping sheath of blinding superheated plasma. The temperature outside the capsule spikes to nearly 5,000 degrees Fahrenheit, roughly half the surface temperature of the sun. Surviving this violent deceleration is an engineering problem we believed we had solved. A solved equation from the Apollo era, etched into the foundational texts of modern aerospace. In late 2022, the Artemis 1 mission concluded its unmanned journey around the moon. As the Orion spacecraft plunged through the atmosphere and drifted down to a picture-perfect splashdown in the Pacific Ocean, the control rooms erupted in applause. The cameras broadcasted a flawless victory to a waiting world. The triumphant return to deep space was no longer a dream. It was a recorded reality. But the truth of space exploration is rarely found in the televised cheers of a control room. It is found weeks later, under the sterile, unforgiving fluorescent lights of a hangar, when the scorched and battered hardware is quietly dissected by the people who built it. When NASA engineers pulled the Orion capsule apart to examine its thermal protection system, the applause abruptly ceased. What they found on the bottom of the spacecraft was an anomaly, a mechanical symptom of a physical reality they did not anticipate. The heat shield, the single most critical barrier standing between human flesh and solar-level incineration, had not behaved according to the computational models. It had not burned away in the smooth, predictable ablation they had calculated. Instead, something far more chaotic had occurred in the dark descent through the atmosphere. It was a discovery that forced an immediate, chilling realization. Artemis 2, the mission destined to carry a crew of 4 back into the terrifying void of lunar orbit, had to be stopped. A flaw so dangerous had been exposed that it threatened to turn our grand return to the moon into an orbital tomb. If you seek the truth hidden within the dark and silent expanses of the cosmos, subscribe and join us on this journey. The universe does not care about our ambitions or our carefully calculated mathematical models. When we dare to cross the threshold into the deep black, the physics that govern reality wait with absolute indifference, ready to expose the fatal fractures in our engineering. To understand the magnitude of what went wrong in the skies above the Pacific Ocean, we must first unlearn a fundamental lie. It is a lie born of common sense, taught to us in our earliest years, and reinforced by our daily interactions with the world. If you ask the average person why a spacecraft burns like a meteor upon re-entering the Earth's atmosphere, they will almost certainly give you the same answer. They will tell you it is because of friction. They imagine the capsule rubbing against the air, much like rubbing your hands together on a cold winter morning to generate warmth. It is a comforting, human-scale concept. But the universe does not operate on a human scale. When we deal with the orbital mechanics of celestial bodies, the intuitive concepts of our everyday reality break down completely. At the edge of space, there is no friction. There is only compression, and it is absolute. When a spacecraft returns from lunar orbit, it hits the upper, gossamer-thin layers of the atmosphere at approximately 25,000 miles per hour. That is nearly Mach 32, 32 times the speed of sound. At these apocalyptic velocities, the air itself becomes a concrete wall. The oxygen and nitrogen molecules resting peacefully in the stratosphere simply do not have the time to move out of the way. They are trapped. The spacecraft slams into them, acting like a gargantuan hypersonic piston. The gas in front of the capsule is crushed. The pressure skyrockets in a fraction of a millisecond. Imagine a snowplow racing down a mountain, but the snow has nowhere to go. It piles up, denser and denser. In the atmosphere, this violent compression forces the mechanical kinetic energy of the falling spacecraft to convert directly into thermal energy. The temperature spikes exponentially. The molecules are squeezed together so violently that the kinetic friction between their atoms causes their chemical bonds to shatter. They are literally torn apart. The heat climbs to 3, then 4, then nearly 5,000 degrees Fahrenheit. The electrons are ripped violently from their nuclei. In an instant, the air ceases to be a gas. It undergoes a phase change into a superheated, electrically charged plasma. A localized star is ignited at the leading edge of the falling machine. This plasma sheath wraps entirely around the spacecraft. It is so dense with charged particles that it acts as a perfect electromagnetic mirror. It absorbs and reflects all radio frequencies. This is why, during the most critical and violent phase of the journey, mission control is met with dead silence. It is the blackout period. For several terrifying minutes, the spacecraft is completely cut off from humanity, plunging through a tunnel of self-generated stellar fire. No telemetry, no voices, just the roaring, indifferent mechanics of the cosmos asserting their dominance. This terrifying wall of thermal energy was not always understood. In the mid-20th century, at the dawn of the space age and the height of the Cold War, the thermal barrier was considered an almost impassable physical law. The early architects of rocketry were building intercontinental ballistic missiles, machines designed to leave the atmosphere and return to deliver devastating payloads. Their initial designs were based on aerodynamic intuition. They built the warheads to look like needles, long, sharp, sleek shapes designed to pierce the atmosphere and slice through the air with minimal resistance. It was a logical assumption. But when they launched these sleek, sharp machines, they melted. The tips absorbed the tremendous heat of aerodynamic compression instantly, liquefying the metal and destroying the vehicles before they could even reach the ground. The sharp point concentrated the thermal load into a microscopic area, turning the tip into a liquid torch. The engineers were trapped in a paradox. The faster they needed to go, the sharper they made the vehicle. The sharper they made the vehicle, the faster it burned. The mathematics of the time suggested that surviving atmospheric re-entry at orbital speeds was a material impossibility. No metal on Earth could withstand the concentrated thermal blast of a hypersonic needle. The paradigm was broken not by a new material, but by a radical shift in perspective. In 1951, an engineer named H. Julian Allen, working at the National Advisory Committee for Aeronautics, the predecessor to NASA, had a profoundly counterintuitive realization. If sharp shapes concentrate heat and destroy the vehicle, what happens if we do the exact opposite? What happens if we make the spacecraft as blunt, flat, and aerodynamically ugly as possible? It was an idea that defied every aerodynamic instinct. A flat object would create massive drag. It would hit the atmosphere like a brick. But Allen's mathematics revealed a hidden mechanism in fluid dynamics. When a blunt object travels at hypersonic speeds, it pushes a massive shockwave ahead of it. Because the object is flat, the shockwave cannot attach directly to the nose of the vehicle. Instead, it detaches. It bows out in front of the spacecraft, leaving a microscopic layer of slightly cooler, slower-moving gas between the superheated plasma and the physical hull of the ship. This detached bow shock is the secret to human survival in space. By creating a blunt, wide profile, over 90% of the agonizing heat generated by atmospheric compression is trapped in the shockwave and carried away by the rushing airflow. The heat never touches the spacecraft. It flows around it. The vehicle uses the atmosphere's own resistance to create a thermal shield made of compressed air. This is why the Apollo capsules, the Soyuz, and the modern Orion spacecraft are not shaped like fighter jets. They are shaped like bells. They are designed not to slice through the air, but to batter it into submission. Yet pushing the shockwave away is only half the battle. The blunt body geometry deflects the vast majority of the thermal energy. But at 25,000 miles per hour, the 10% of the heat that does penetrate the boundary layer is still more than enough to turn aerospace-grade aluminum into a bubbling liquid and incinerate the crew inside. To survive the remaining heat, you cannot simply build a thicker wall. You cannot outbuild the thermodynamic fury of the universe. Instead, you must build a wall designed to die. This is the grim and elegant science of ablation. The heat shield on the bottom of a returning capsule is not designed to permanently block heat like the insulation in a house. It is a sacrificial altar. It is engineered to be consumed, to bleed the heat away through its own destruction. The material is subjected to temperatures so extreme that it skips the liquid phase entirely. The surface of the shield sublimates, turning directly from a solid into a gas. For the Orion capsule, as it was for the Apollo missions, the material chosen for this monumental task is a highly classified, incredibly complex chemical matrix known as AVCoat. It is not poured or molded. It is injected, by hand, into more than 300,000 individual hexagonal cells of a fiberglass honeycomb structure. This meticulous, agonizingly slow manufacturing process creates a surface of unparalleled thermal resistance. When the Orion capsule hits the atmosphere, the AVCoat undergoes a violent chemical transformation known as pyrolysis. As the plasma licks the surface of the shield, the epoxy resin absorbs the thermal energy. It uses that energy to violently break its own molecular bonds. The material darkens, chars, and then vaporizes. But this destruction is highly controlled. As the resin turns into a superheated gas, it violently expands outward, pushing against the incoming plasma. This outgassing creates a secondary boundary layer, a cool, microscopic breeze of dying carbon molecules that physically pushes the sun-like temperatures away from the pristine metal of the crew cabin. It is a beautiful, violent ballet of thermodynamics. The spacecraft sweats away its own skin to keep the internal temperature at a comfortable 72 degrees. By the time the capsule deploys its parachutes, the heat shield is deeply scarred, charred black, and significantly thinner, having sacrificed thousands of pounds of its own mass to the atmosphere. But it survives. This blunt body ablative architecture was the crowning triumph of the Apollo era. It was the solved equation that allowed humans to leave the immediate vicinity of Earth and venture into the deep dark. We mastered the geometry. We mastered the chemistry. We went to the moon and we came back, riding fiery meteors of our own design. It became an accepted foundational truth of aerospace engineering, a closed chapter in the history of physics. But the universe punishes assumption, and it is utterly merciless when it comes to the mathematics of kinetic energy. There is a profound, terrifying difference between falling from low Earth orbit, like a capsule returning from the International Space Station, and falling from the moon. The International Space Station orbits at roughly 250 miles above the Earth. Returning from that altitude requires a spacecraft to bleed off a velocity of about 17,500 miles per hour. That is incredibly fast, and the thermal loads are immense. But returning from the moon requires falling from a distance of 240,000 miles. By the time the Earth's gravity pulls the capsule back into the atmosphere, it has accelerated to 25,000 miles per hour. To the layman, this might seem like a simple linear increase. It is roughly 40% faster. One might logically assume that the heat shield simply needs to be 40% thicker, or that the thermal temperatures will be 40% hotter. But physics is governed by exponential laws. The equation for kinetic energy is one of the most uncompromising rules of our reality. The energy of a moving object is equal to half of its mass multiplied by the square of its velocity. It is that final variable, the velocity squared, that builds the trap. Because the speed is multiplied by itself, a 40% increase in velocity does not result in a 40% increase in kinetic energy. It nearly doubles it. When Orion returns from the moon, it carries almost twice the destructive energy of a vehicle returning from low Earth orbit. That energy must be violently shed in the exact same amount of time, through the exact same corridor of atmosphere. The temperatures do not scale gently. They spike violently. The pressure waves do not just push, they crush with exponential force. At Mach 32, the margins for error do not just shrink, they evaporate entirely. The difference between a safe return and catastrophic incineration becomes thinner than a single strand of human hair. At these extremes, the materials we build are pushed to the absolute jagged edge of their physical and chemical limitations. For 50 years, the aerospace community believed they understood exactly where that jagged edge was. The architects of the Artemis program, tasked with returning humanity to the lunar surface, did not believe they needed to invent a new paradigm for re-entry. They possessed half a century of accumulated data. They resurrected the AVCoat chemistry, updating it with modern manufacturing techniques. They utilized the largest, most powerful supercomputers on Earth to run advanced computational fluid dynamic simulations. They ran trillions of calculations, mapping the Navier-Stokes equations across millions of data points. They predicted every vector of heat, Every pressure node, every microscopic layer of plasma. Artemis 1, the uncrewed test flight, was supposed to be a mere formality. It was designed to be a physical validation of a mathematical certainty, a final checkmark before putting human beings inside the capsule. The engineers fired the Orion spacecraft at the Earth with the absolute, unshakable confidence of a species that believed it had conquered the thermal abyss. They watched the telemetry as Orion slammed into the atmosphere. They watched the trajectory hold true. They watched the parachutes deploy perfectly. They watched the capsule bob gently in the Pacific Ocean, its charred exterior looking exactly as it was supposed to look from the distance of a recovery helicopter. The models had seemingly predicted reality with flawless precision. But mathematical models are pristine, sterile abstractions. They are isolated from the chaotic, vibrating brutality of the physical universe. When the engineers finally brought the Orion capsule into the hangar, placed it under the harsh light of the inspection lamps, and looked closely at the charred remains of the avcoat, they realized the universe had hidden a variable from them. The shield had survived, but it had not behaved according to the sacred equations. It had not gracefully sublimated layer by microscopic layer. It had not bled away the heat in a smooth, predictable ballet of outgassing. The physical reality of the material had broken from the digital simulation. Something deep within the ancient, settled science of ablation was fundamentally, terrifyingly wrong. And as they peered closer at the damaged heat shield, they realized that if there had been astronauts inside that capsule, their lives would have hung by a frayed and unpredictable thread. To understand the cold dread that settled over the engineers in the recovery hangar, we must look closer at the charred remains of the Orion spacecraft. Picture the scene. The massive, cone-shaped capsule sits elevated on a steel scaffolding, stripped of its ocean-soaked flotation collars. It smells of ozone, burnt carbon, and the sharp metallic tang of the ocean. Under the blinding white glare of halogen inspection lamps, a team of technicians in sterile suits slowly circles the base of the vehicle. They are armed with laser scanners, high-resolution macroscopic cameras, and ultrasonic thickness gauges. They are mapping the topography of a battlefield where human engineering fought a brutal, silent war against the thermodynamics of the solar system. What they expected to find was a surface worn smooth by the fire of re-entry. The mathematical models, the trillion lines of code executed on supercomputers, predicted a uniform degradation. The avcoat material should have ablated away in a microscopic layer-by-layer sublimation, leaving behind a pristine, evenly charred crust, much like the smooth, blackened surface of a marshmallow toasted perfectly over a steady flame. The heat shield is designed to lose mass, but it is designed to lose it predictably, shedding its skin in a gentle, highly controlled outgassing that keeps the superheated plasma at bay. Instead, the lights illuminated a jagged, violent landscape. The bottom of the Orion capsule was not smooth. It was scarred by deep, erratic gouges. Across the massive 16-foot diameter of the heat shield, there were craters. Entire chunks of the avcoat material had not gracefully sublimated. They had violently broken off. Pieces the size of a human fist, and sometimes larger, had cracked, separated from the fiberglass honeycomb matrix, and been ripped away by the hypersonic slipstream. In the sterile nomenclature of aerospace engineering, this catastrophic physical failure is known as spalling. But a technical term does not capture the terrifying reality of what spalling represents at Mach 32. Imagine you are driving down a highway at night, relying on a thick, protective windshield to keep the freezing wind and debris out of your car. Ablation is the slow, even frosting of that glass, slightly reducing your visibility, but keeping the integrity of the barrier intact. Spalling is someone throwing a brick at the windshield, shattering a jagged hole through which the freezing gale violently rushes in. When a heat shield spalls, it violates the most critical requirement of hypersonic flight: aerodynamic stability. The survival of a spacecraft during re-entry depends entirely on maintaining a smooth boundary layer. The air flowing over the blunt body of the capsule must remain in what physicists call laminar flow. Laminar flow is orderly, stratified, and predictable. It creates that microscopic cushion of cooler air that insulates the hull from the detached shockwave. But when a chunk of the heat shield breaks off, it leaves behind a cavity, a pothole in the skin of the spacecraft. When the hypersonic airflow hits that sudden crater, the laminar flow is instantly shattered. The air tumbles. It swirls into the depression, creating violent, chaotic vortices. This is turbulent flow. And in the context of plasma dynamics, turbulence is a localized apocalypse. A vortex of 5,000-degree plasma trapped inside a cavity on a heat shield does not simply wash over the surface. It burrows. It begins to spin, acting like a superheated electromagnetic drill bit. It concentrates the thermal load into a microscopic point, driving the heat deeper and deeper into the underlying structure. If a spalling crater forms too early in the re-entry process, or if it grows too deep, the plasma drill will breach the final layers of the avcoat, melt through the titanium skeleton of the capsule, and instantly incinerate everything inside. The technicians staring at the craters on Orion's underbelly knew exactly what those jagged holes meant. The vehicle had survived, yes, but it had survived only because the universe had been statistically merciful. If those chunks had liberated themselves just a few minutes earlier during the peak heating phase, or if a few more chunks had broken away in the same quadrant, the plasma vortices would have reached the crew cabin. The triumphant splashdown would have been replaced by a silent, invisible scattering of ash in the upper stratosphere. The engineers were now staring into a profound void of understanding. They had terabytes of data from the flight. The heat shield was embedded with hundreds of microscopic thermocouples and radiometers, sensors designed to record the exact temperature and pressure at varying depths within the avcoat material. When the data analysts downloaded the telemetry, they did not find answers. They found a cacophony of contradictions. The sensors recorded massive, unexpected spikes in temperature in localized regions, perfectly corresponding to the areas where the spalling had occurred. The mathematical models had projected a smooth curve of heating and cooling. The reality was a jagged, erratic seismograph of thermal violence. The sheer scale of the mystery began to expand, threatening to dismantle decades of established aerospace doctrine. The avcoat material was not an experimental, untested compound. It was the absolute gold standard of thermal protection. It was the exact same chemical foundation that had brought the Apollo astronauts safely home from the moon in the 1960s and 70s. During the Apollo program, the avcoat heat shields had performed with legendary reliability. They had ablated exactly as designed, returning the command modules with smooth, evenly charged surfaces. How could a material that conquered the lunar return 50 years ago suddenly fail today? The laws of thermodynamics had not changed in half a century. The atmosphere of the Earth had not altered its chemical composition. The velocity of a lunar return was exactly the same. So why was Artemis 1 shedding its armor like a crumbling ancient ruin? To unravel this paradox, we must look at the invisible, microscopic scale of manufacturing and the hubris of modern industrial efficiency. During the Apollo era, the heat shield was a masterpiece of agonizing manual labor. The underlying structure of the shield is a gigantic honeycomb made of fiberglass. Inside this honeycomb are roughly 330,000 individual hexagonal cells. In the 1960s, a small army of technicians armed with specialized caulking guns filled each one of these microscopic cells by hand. It was a tedious, grueling process that took months to complete. Each cell was individually packed with the avcoat resin, cured, and then subjected to X-ray inspection. If a single cell had a void or an air bubble, it was drilled out and refilled. This manual process created a heat shield that was structurally continuous, bound together by the sheer, exhaustive rigor of human hands. But when the Artemis program was resurrected, NASA and its contractors sought to modernize the manufacturing process. The manual injection of 330,000 cells was deemed too slow, too expensive, and too archaic for the 21st century. Instead, they developed a new automated technique. They manufactured the avcoat in large solid blocks. These blocks were then precisely machined by computer-controlled routers into massive curved puzzle pieces. These prefabricated blocks of avcoat were then glued and bonded directly onto the underlying carbon fiber and titanium skeleton of the Orion capsule. It was faster. It was more efficient. It looked flawless on the factory floor. But spaceflight does not care about factory floor efficiency. It only cares about structural integrity under extreme dynamic loads. The engineers began to formulate a terrifying hypothesis. Had the modern manufacturing process fundamentally compromised the mechanical strength of the material? When a solid block of avcoat is bonded to a metal skeleton, it creates macroscopic seams. It creates boundary lines between the blocks. More importantly, the internal stress of the material behaves differently. During the violent deceleration of re-entry, the spacecraft is not just subjected to 5,000 degrees of heat, it is subjected to massive, crushing G-forces. The capsule vibrates, compresses, and groans under the aerodynamic pressure. Perhaps, the engineers theorized, the new block-molded avcoat could not handle the sheer mechanical flexing of the spacecraft. Perhaps the thermal shock of the plasma combined with the physical crushing force of the atmosphere caused the internal structure of the blocks to fracture. Once a microfracture formed deep within the material, the trapped gases from the sublimating resin would have nowhere to go. The pressure inside the crack would build instantly until it detonated like a miniature bomb, blowing a fist-sized chunk of the shield out into the slipstream. But this theory, as logical as it seemed, could not be easily proven. The physics of hypersonic re-entry are impossible to perfectly replicate on the surface of the Earth. This is the great silent barrier of aerospace engineering. When we design a car, we put it in a wind tunnel and blow air over it at 100 miles per hour. We can measure every aerodynamic force with perfect clarity. But you cannot build a wind tunnel that blows air at Mach 32. No fan on Earth can spin fast enough. No compressor can generate that level of continuous pressure. To test heat shields on the ground, engineers rely on facilities called arc jet testing centers. An arc jet is a massive, terrifying machine that attempts to simulate the thermal conditions of re-entry. It uses colossal amounts of electricity to rip the electrons off gas molecules, creating a localized beam of plasma. The material sample is placed in a vacuum chamber, and the plasma beam is fired at it. It is as close to touching a star as humanity can engineer in a laboratory. But an arc jet has severe, crippling limitations. It can only produce the required temperatures for a few minutes at most before the electrodes melt and the facility destroys itself. Furthermore, it can only test small, localized samples of material. You can put a 4-inch puck of avcoat into an arc jet, but you cannot put an entire 16-foot diameter heat shield into the chamber. You cannot simulate the massive, overarching aerodynamic pressure waves that wrap around the entire vehicle. You cannot simulate the deep structural flexing of the titanium hull underneath the shield. For decades, engineers relied on a dangerous mathematical bridge called extrapolation. They tested small samples in the arc jet, measured how they ablated, and then fed that data into supercomputers. The algorithms took the behavior of a 4-inch puck and multiplied it mathematically to predict the behavior of a 16-foot shield. In the realm of linear physics, extrapolation is a safe, reliable tool. But fluid dynamics and thermodynamics at Mach 32 are not linear. They are chaotic. They are governed by fractal complexities where the slightest deviation at the microscopic level cascades into catastrophic failures on the macro scale. The arc jet testing validated the chemistry of the avcoat. It proved that the material would sublimate, but it was entirely blind to the mechanical spalling. The ground tests could never predict that the material would simply break apart under the unique, localized pressures of the Artemis flight path. This brought the investigation to the most crucial and perhaps most terrifying variable of all. The difference was not just in the manufacturing of the heat shield. The difference was in the very path the spacecraft took to return to Earth. When the Apollo astronauts returned from the Moon, they executed a direct ballistic re-entry. They hit the atmosphere at a steep angle, plunging straight down into the thickening air. It was a brutal, bone-crushing descent. The astronauts were subjected to intense G-forces, sometimes peaking at 10 or 11 times the force of gravity. The heat spike was absolute, sudden, and terrifyingly brief. The capsule plunged through the fire in a matter of a few minutes, bleeding off all 25,000 miles per hour of velocity in one agonizing, singular dive. But the architects of the Artemis program wanted to change this. They wanted a gentler, more precise return. The goal of Artemis is not just to plant a flag and return home. It is to build a sustainable, continuous presence in deep space. That requires launching a wider variety of crew members, not just peak-condition test pilots who can withstand 11 Gs. It also requires the ability to pinpoint the landing zone with extreme accuracy, regardless of where the Moon is positioned relative to the Earth at the time of departure. To achieve this, orbital mechanics dictated a radical new maneuver, the skip re-entry. Instead of plunging straight down, the Orion spacecraft was programmed to hit the upper atmosphere at a slightly shallower angle. It would descend into the stratosphere, using the friction of the thin air to brake, bleeding off a significant portion of its velocity. But then it would do something fundamentally bizarre. Using the aerodynamic lift generated by the asymmetrical shape of the capsule, it would pitch up. It would physically bounce off the thickening atmosphere, like a flat stone skipping across the surface of a pond. The capsule would literally fly back out of the atmosphere, ascending back into the frozen vacuum of space for a brief period. It would arc over the Earth in a suborbital trajectory, cooling down in the absolute zero of the void, before finally plunging back down for its second, final descent into the Pacific Ocean. This skip re-entry was a masterpiece of orbital navigation. It reduced the peak G-forces on the crew to a much more manageable level. It extended the flight path, allowing the spacecraft to glide for thousands of miles across the globe, giving mission control the ability to steer the capsule to a precise landing zone off the coast of California. Mathematically, it was elegant. Thermodynamically, it may have been a trap. The heat shield of a returning spacecraft is designed to survive a single, overwhelming spike of thermal energy, but the skip re-entry subjects the shield to something far more insidious: thermal shock. During the first dip into the atmosphere, the avcoat is blasted with plasma. The surface instantly sublimates, the material chars, and the internal temperatures skyrocket. Then, the spacecraft skips back out into the void. In a matter of seconds, the roaring fire is replaced by the freezing, silent vacuum of space. The outer layer of the charred, chemically altered avcoat rapidly cools and contracts. Then, minutes later, the spacecraft plunges back into the atmosphere for the second time. The cooling, contracting material is suddenly, violently hit with a second blast of hypersonic plasma. The material expands again, violently. Imagine taking a thick glass bowl, heating it in an oven until it is glowing red, then plunging it into a bath of liquid nitrogen, and then immediately throwing it back into the fire. The glass will not melt. It will shatter. It will spall. The engineers poring over the telemetry from Artemis 1 stared at the thermal graphs, watching the jagged lines peak, drop, and peak again. They looked at the fractured craters on the physical hull of the capsule. The terrifying realization began to crystallize. The massive, complex supercomputers, the trillions of calculations, the decades of legacy data, none of it had properly accounted for the physical reality of how this specific composite material would react to the violent thermal whiplash of a skip re-entry. They had built a machine designed to survive the fire, but they had not anticipated that the fire itself would be delivered in a rhythmic, pulsing assault that could physically tear the armor apart. The scale of the mystery was no longer a matter of a few missing chunks of material. It was a fundamental breakdown in our understanding of how solid matter behaves when subjected to the extreme, kinetic brutality of the cosmos. And standing in the hangar, looking at the wounded machine, the engineers knew that until they solved this paradox, until they understood exactly why the universe was ripping their heat shield apart, no human being could ever step foot inside an Orion capsule. The path back to the Moon was barred not by a lack of rocket fuel, but by a terrifying microscopic misunderstanding of the physical world. To truly grasp the nightmare unfolding within the Artemis program, we must confront the barrier where human mathematics disintegrates into physical chaos. For decades, the aerospace industry has worshipped at the altar of computational fluid dynamics. We have convinced ourselves that if a computer is powerful enough, if the algorithms are elegant enough, we can predict the behavior of the universe before it even happens. We rely on a set of mathematical rules known as the Navier-Stokes equations. These are the fundamental laws of fluid motion. They describe how gases flow, how pressure distributes, and how heat transfers across a surface. They are the invisible architecture of modern engineering. used to design everything from the wings of a commercial airliner to the shape of a Formula One race car. But there is a dark, widely acknowledged secret within the realm of theoretical physics. The Navier-Stokes equations cannot be solved exactly. For over a century, the greatest mathematical minds on Earth have failed to find a perfect, analytical solution for turbulent flow. It remains one of the million-dollar Millennium Prize problems, an unyielding wall of mathematical complexity. Because we cannot solve the equations perfectly, we approximate. We use supercomputers to break the airflow around a spacecraft into millions of tiny digital cubes, calculating the approximate conditions within each cube and assuming how they interact with their neighbors. In the gentle subsonic world of commercial aviation, these approximations are brilliant. They are more than enough to ensure safety. But a spacecraft returning from lunar orbit does not exist in a gentle world. It exists at the absolute boundary of physics. At Mach 32, the air is not just flowing, it is chemically reacting. It is breaking apart, ionizing, and forming a plasma that carries its own electromagnetic fields. The heat transfer is not just convective, it is radiative, meaning the glowing plasma is actively shining thermal energy directly into the atomic structure of the heat shield, like a miniature sun. When you feed these extreme, non-linear variables into the Navier-Stokes approximations, the algorithms begin to hallucinate. The supercomputers, capable of calculating billions of floating-point operations per second, are essentially guessing. They are trying to predict the behavior of a chaotic, turbulent plasma vortex using a mathematical net that is fundamentally flawed. The engineers looking at the torn underbelly of the Orion capsule realized that their digital oracle had lied to them. The simulated spacecraft had survived. The physical spacecraft was bleeding. This is the great paradox of modern aerospace design. We have built machines so complex and pushed them into environments so extreme that our most advanced mathematics can no longer accurately predict their survival. We are flying blind, guided only by the ghosts of simulations. To understand why the mathematics failed so spectacularly, we have to zoom in. We must abandon the macro scale of the 16-foot capsule and dive into the microscopic, granular architecture of the avcoat material itself. The heat shield is not a solid sheet of metal. It is not a uniform block of ceramic. It is a wildly complex, heterogeneous composite designed to perform contradictory tasks simultaneously. Imagine a microscopic battlefield. The foundation of avcoat is a honeycomb matrix made of woven fiberglass. This is the skeleton. It is designed to provide structural rigidity, to hold the shape of the shield against the crushing aerodynamic pressures of re-entry. Injected into every single cell of this honeycomb is a proprietary concoction, an epoxy Novolac resin mixed with microscopic spheres of silica glass and phenolic microballoons. These microballoons are hollow, infinitely small spheres of plastic. The material is essentially an engineered paradox. It must be strong enough to survive the violent vibrations of a multi-million-pound rocket launch without cracking. Yet it must be fragile enough to smoothly burn away or ablate when exposed to 5,000 degrees. It is an impossible compromise. When the plasma from atmospheric re-entry licks the surface of this composite, a violent, multi-stage chemical war begins. First, the intense heat penetrates the outer layer. The epoxy resin reaches its boiling point almost instantly, but because it is trapped within the solid matrix, it cannot simply boil away. It undergoes pyrolysis, chemically decomposing into a superheated gas. This gas rapidly expands, building immense internal pressure. It forces its way out through the microscopic pores of the material, rushing toward the surface. This is the outgassing that pushes the external plasma shockwave away from the ship. As the resin vaporizes and escapes, it leaves behind a skeleton of charred carbon. This is the char layer. It is black, brittle, and highly porous. It acts as an incredible insulator, preventing the extreme heat from penetrating deeper into the virgin avcoat below. As the re-entry progresses, this char layer grows thicker, pushing deeper and deeper into the material, while the extreme outer surface slowly erodes away into the slipstream. This is how it is supposed to work. This is the smooth, predictable ablation modeled by the supercomputers. But this idealized model completely ignores the brutal mechanical reality of thermal expansion. Every material in the universe expands when it is heated and contracts when it is cooled. But different materials expand at different rates. This is the coefficient of thermal expansion. Inside the AV coat, you have fiberglass, epoxy resin, silica, and phenolic microballoons, all bonded tightly together. When the extreme heat of re-entry strikes, the resin desperately tries to expand, swelling under the massive thermal load. But the fiberglass honeycomb skeleton resists. It expands at a much slower rate. This creates immense invisible shear stresses deep inside the material. The composite is literally tearing itself apart from the inside out. In a traditional direct descent like the Apollo missions, the spacecraft plunges through the atmosphere so quickly that this internal war is over before it can become catastrophic. The intense heat vaporizes the material before the internal stresses can fully fracture the solid block. The ablation outpaces the mechanical failure, but Artemis 1 did not execute a direct descent. It executed a skip re-entry, and this orbital maneuver weaponized the internal stress of the AV coat. Consider the sequence of events. The Orion capsule hits the atmosphere for the first time. The temperature spikes to nearly 5,000 degrees. The surface of the AV coat begins to pyrolyze. The char layer forms. The internal materials begin their desperate tug of war, the resin expanding against the restricting fiberglass. The stress levels deep within the composite reach a critical threshold. Then, the capsule pitches up. It uses aerodynamic lift to fly back out of the atmosphere, ascending back into the frozen void of suborbital space. Instantly, the 5,000-degree plasma vanishes. It is replaced by the silent, absolute cold of space. The outer char layer, glowing red-hot just seconds before, is plunged into an environment hundreds of degrees below zero. It rapidly cools and violently contracts. But the heat has already soaked deep into the inner layers of the virgin AV coat, meaning the core of the heat shield is still expanding while the outer shell is aggressively shrinking. The thermal gradient is inverted in a matter of seconds. Imagine a massive, thick sheet of ice placed over a boiling cauldron of water. The tension is unsustainable. Deep within the heat shield, microscopic fissures begin to form. The bonds between the fiberglass and the resin snap in the dark silence of space. Voids are created. The structural integrity of the composite is fundamentally shattered. 10 minutes later, the capsule plunges back into the atmosphere for its final descent. The freezing, fractured surface is suddenly hit with a second massive wave of hypersonic plasma. The gas trapped inside the newly formed microscopic fissures instantly superheats and violently expands. But now, the outer char layer is brittle and compromised. It cannot hold the pressure. The material detonates from within. This is the mechanical spalling that horrified the engineers in the recovery hangar. Entire chunks of the compromised char layer and virgin material below it, weakened by the deep freeze of the skip maneuver, were violently blown outward by expanding gases. The smooth aerodynamic profile was destroyed. Craters formed, and the hypersonic plasma rushing over the damaged hull at Mach 25 dove into those craters, swirling into superheated vortices that threatened to drill straight through to the crew cabin. The engineers had walked blindly into an invisible trap. They had taken a legacy material designed for a continuous localized burn, manufactured it in modern monolithic blocks that changed its internal stress distribution, and then subjected it to a trajectory that rhythmically tortured its chemical structure. The math had failed because the math was not designed to account for the chaotic synergy of thermal shock, modern manufacturing adhesives, and the deep freeze of a suborbital skip. This realization brought the Artemis program to a grinding, shuddering halt. The paradox was fully formed, and the barrier to human exploration was no longer celestial, it was structural. The dilemma they faced was paralyzing. If the AV coat material was fundamentally incompatible with the skip re-entry profile, what were the options? The most obvious solution to a layman would simply be to change the material, invent a new heat shield. But in the suffocatingly slow, risk-averse world of modern aerospace, changing a critical component like the thermal protection system is not a matter of months. It is a matter of decades. To develop an entirely new ablative composite requires starting from zero. It requires formulating new chemistry, running thousands of material coupon tests, building new manufacturing facilities, and executing entirely new uncrewed test flights. It would cost billions of dollars and delay the return to the moon into the late 2030s, if not entirely killing the political will to continue the program. The alternative, then, is to keep the material but change the trajectory. Abandon the elegant, fuel-efficient skip re-entry and revert to the brutal direct descent of the Apollo era. But doing so would require an entire redesign of the mission profile. It would severely limit the launch windows, drastically reduce the precision of the splashdown, and subject the modern, heavier Orion capsule to G-forces that might compromise its internal life support systems. The entire architecture of the Artemis program, designed for sustainable, continuous lunar operations, was built entirely around the skip maneuver. Pulling that thread would unravel the entire mission design. The engineers were trapped in a technological purgatory. They could not change the material without losing a decade. They could not change the trajectory without breaking the mission parameters. And they absolutely could not fly human beings on a heat shield that was shedding its armor like broken glass. They had to find a way to fix the avcoat they already had. But how do you fix a chemical and mechanical failure that you cannot accurately test on Earth? This is the ultimate barrier, the cruelest joke played by the laws of physics. As previously established, there is no facility on the planet capable of replicating the exact conditions of a lunar return. The ArcJet facilities can blast small samples with plasma, but they cannot simulate the deep, structural flexing of a 16-foot capsule undergoing the brutal deceleration of re-entry. They cannot simulate the exact sequence of extreme heating, immediate deep freezing, and secondary heating. They can only test fragments in isolated, controlled conditions. The engineers are forced to rely on extrapolation. They are forced to take data from small, flawed tests and run it through the exact same mathematical models that failed them the first time. They have to tweak the algorithms, attempting to artificially inject the chaos of spalling into the code. They must try to simulate the microscopic fractures, the internal void pressures, and the tumbling plasma vortices. But simulating chaos is fundamentally impossible. It is a contradiction in terms. You cannot predict the exact moment and location a piece of brittle char will break away. You cannot calculate the precise depth of a plasma drill entering an unpredictable crater. The engineers are reduced to calculating probabilities. They are essentially rolling a digital pair of dice, running millions of Monte Carlo simulations to see how often the thermal damage reaches the critical threshold of the titanium hull. They are attempting to prove through the sheer brute force of statistics that even if the heat shield spalls again, it will not spall deep enough to kill the crew. They are trying to find a mathematical justification for an acceptable level of catastrophic physical failure. Imagine being an astronaut, strapping yourself into a machine sitting atop 3,000 tons of highly explosive liquid hydrogen. You are about to be hurled 250,000 miles into the crushing, irradiated silence of deep space. You place your life entirely in the hands of the engineers below, and those engineers must look you in the eye and admit that the only thing protecting you from instant blinding incineration is a piece of mathematics that they already know is flawed. They must admit that the shield will break, that pieces will tear away, and that they are simply betting the odds that it won't break too deeply. The certainty of the Apollo era, the absolute confidence in the physical machinery, is gone. It has been replaced by a grim, statistical gamble. The return to the moon is no longer a triumphant march of engineering supremacy. It has become a terrifying negotiation with the thermal abyss. A negotiation where the universe holds all the leverage and our only defense is a shattered model of an unpredictable reality. The deeper they peer into the charred topography of the Orion capsule, the more the void stares back, mocking the fragile, arrogant assumptions of human science. When the space agency officially announced the delay of the Artemis II mission, pushing the timeline deeper into an uncertain future, the press releases spoke in the sanitized, reassuring language of public relations. They cited an abundance of caution. They spoke of an unwavering commitment to crew safety and the necessity for further, rigorous data analysis. It was a message meticulously designed to soothe the public, to project an image of steady, methodical progress. But behind the closed doors of the thermal analysis labs, away from the cameras and the political oversight, the reality is far more chilling. A delay of this magnitude in this specific context is not a mere bureaucratic hiccup or an issue of terrestrial supply chains. It is a silent, profound admission that humanity has collided with an invisible, uncompromising wall. We are not merely trying to fix a broken component. We are grappling with a fundamental reckoning. The halting of Artemis 2 exposes a terrifying vulnerability in our entire philosophy of modern engineering, and by extension, our long-term future as a spacefaring species. The hidden consequence of the Orion heat shield anomaly stretches far beyond the immediate physical return to the lunar surface. It strikes at the very heart of how we comprehend the physical universe and our assumed, triumphant destiny within it. For the last half-century, we have operated under a grand, comforting illusion. We convinced ourselves that we had tamed the cosmos with silicon and code. We believed that the sheer computational power of our modern supercomputers could act as a bridge across the vast gaps in our physical understanding. If we could not build a wind tunnel on Earth to test the apocalyptic fires of Mach 32, we believed we could simply simulate it, mapping the thermodynamic fury of the universe into neat, predictable algorithms. We believed that reality could be digitized, controlled and conquered from a glowing monitor on a desk. The sudden, chaotic spalling of the AV-coat material shattered that illusion completely. It revealed a cold, undeniable truth. The universe is analog, and it is infinitely fractally complex. The digital models are not the territory. They are merely a map drawn by a species that is fundamentally blind to the deepest mechanics of reality. When a supercomputer predicts the flow of hypersonic plasma, it is performing an act of mathematical approximation. But the plasma itself does not approximate. The heat does not average itself out. The mechanical stress shearing inside a composite honeycomb structure does not care about statistical probabilities. It acts with absolute brutal physical determinism. By revealing the fatal flaw in our models, the Orion capsule has forced us to confront a complexity ceiling. We have pushed our technology into a realm so extreme, so violent, that our ability to predict the outcome has fundamentally broken down. We are no longer engineers building a sturdy bridge over a predictable river. We are gamblers throwing a fragile construct of metal into a localized manifestation of hell, hoping the cosmic dice land in our favor. This realization casts a long, dark shadow over the entire concept of deep space exploration. The moon is our closest celestial neighbor. It is our cosmic backyard. The 25,000-mile-per-hour return velocity is the absolute bare minimum required for true interplanetary travel. It is the entry fee to the solar system. If we are struggling to survive the physics of this minimal threshold, if we are trapped by the thermodynamics of our own local neighborhood, what does this mean for our grander ambitions? Consider the long-stated, romanticized goal of landing human beings on Mars. The red planet is an order of magnitude more difficult, more unforgiving, and more violently opposed to human intrusion. The Martian atmosphere is a cruel physical paradox. It is incredibly thin, less than 1% the density of Earth's atmosphere. It is far too thin to provide the massive aerodynamic drag necessary to easily slow down a heavy, multi-ton crewed spacecraft. You cannot simply deploy traditional parachutes. The vehicle would slam into the bedrock at supersonic speeds. Yet, despite being thin, the atmosphere is just thick enough to generate catastrophic incinerating heat through hypersonic compression. To land a massive payload on Mars, we cannot use a simple blunt body capsule. The physics do not scale. We will need entirely new, unfathomably large inflatable aerodynamic decelerators or massive retro-propulsion systems firing directly into the incoming hypersonic plasma and returning from Mars. That requires plunging back into Earth's atmosphere not at 25,000 miles per hour, but at speeds exceeding 35,000 miles per hour. Remember the unforgiving mathematics of kinetic energy. The velocity is squared. A 35,000 mile per hour return does not just linearly increase the heat, it multiplies the destructive energy exponentially, pushing the thermal loads far beyond the melting point of almost any known substance. The anomaly discovered on the scarred underbelly of the Orion spacecraft is not an isolated lunar problem. It is a dark omen for Mars. It is a stark warning that the thermodynamics of planetary entry scale violently, and that the materials we currently possess, the chemistry we currently understand, may simply be incapable of surviving the journey. We are looking at a future where our rockets are powerful enough to take us anywhere, but the physics of deceleration permanently bar us from ever coming back alive. This leads to an even more chilling existential consideration. When we look up at the night sky, we are confronted by a silent, seemingly empty void. This is the Fermi paradox. With hundreds of billions of galaxies, each containing hundreds of billions of stars, the universe should be teeming with intelligent life. We should see the thermal signatures of their vast engineering projects, the radio echoes of their communications, the physical evidence of their interstellar empires. Yet, there is nothing. Just an overwhelming, deafening silence. For decades, scientists and philosophers have theorized the existence of a great filter, a universal barrier that prevents civilizations from expanding beyond their homeworld. We typically imagine these filters as dramatic, self-inflicted apocalypses, the invention of nuclear weapons, the creation of uncontrollable artificial intelligence, or the slow, suffocating collapse of an ecological biosphere. We imagine intelligent species destroying themselves in bursts of hubris and violence, but the universe is rarely so poetic. It is governed by unfeeling laws. The scorched, fractured geometry of the Orion heat shield suggests a great filter that is far more terrifying because it is entirely mundane. What if the barrier to the stars is not a dramatic failure of morality or politics, but a simple, brutal law of thermodynamics? What if the universe has structurally quarantined us? The energy required to climb out of a planetary gravity well is immense, requiring controlled explosions of millions of pounds of chemical propellant. But leaving is only half the equation. The kinetic energy penalty for returning, the sheer inescapable necessity of bleeding off orbital velocity through atmospheric compression, acts as a thermodynamic executioner. Perhaps this is the fate of countless civilizations scattered across the dark matter web of the cosmos. They evolve. They look up at the stars. They build their massive launch vehicles. They invent their supercomputers, run their fluid dynamic simulations, and launch their proud, blunt-bodied ships into the black. And then they watch them burn upon return, betrayed by the chaotic spalling of their own heat shields, trapped by the nonlinear math of thermal shock. The atmosphere, the very thing that nurtured our evolution, the delicate blanket of gas that shields us from solar radiation and provides the oxygen for our first breaths, becomes an impenetrable membrane. It is a one-way mirror. It allows us to look out, but it exacts an agonizing, fiery toll if we ever try to return. We may not be a species destined for the stars. We may simply be a localized biological phenomenon, permanently locked inside a thermodynamic prison of our own planet's design. And in the present day, there are 4 human beings living with the weight of this realization. The crew assigned to Artemis 2. They are seasoned test pilots, brilliant scientists, and individuals of unparalleled psychological resilience. They spend their days in simulators, practicing orbital rendezvous maneuvers, studying lunar geology, and preparing for the greatest adventure of the 21st century. But they are not ignorant of the reality resting in the hangars. They know exactly what the engineers found. They understand the mathematics of spalling, the chaotic vortices of plasma, and the crippling limitations of the arc jet testing facilities. They know that the delay is not a guarantee of a perfect fix. There is no perfect fix. There is no magic material that can be conjured into existence overnight to replace the AV coat without delaying the program for decades. When the Artemis 2 mission is finally cleared for launch, it will not be because the engineering problem was perfectly, physically solved. It will be because the probabilistic models have been adjusted. The engineers will calculate an acceptable margin of risk. They will run millions of simulated re-entries, mapping the statistical likelihood of a plasma drill breaching the hull. They will determine that the odds of survival are sufficiently high to justify the launch. And then, they will ask 4 human beings to strap themselves into a machine that relies entirely on that compromised math. This is the ultimate, hidden consequence of the Artemis 1 anomaly. It is a fundamental shift in the psychological contract of space exploration. It demands that we stop pretending we have mastered the universe. It demands that the astronauts going back into the deep black accept a level of calculated, inescapable dread. They must accept that their survival depends not on the absolute certainty of human engineering, but on a statistical gamble against an indifferent cosmos. They are being asked to ride a wounded machine into the fire, knowing that the armor protecting them is fundamentally flawed, and that the only thing standing between them and the thermal abyss is a fragile, untested hope that the universe will be merciful a second time. The countdown has been paused, but the void remains. It does not care about our timetables, our budgets, or our desperate evolutionary need to conquer the unknown. It simply waits, governed by the cold, eternal mechanics of energy and mass, ready to test the very limits of our sanity. When you walk outside tonight and look up at the moon hanging pale and silent in the sky, it is no longer just a celestial companion. It is a monument to our limitations. For half a century, we looked at that cratered surface as a conquered summit, a dusty relic of the Apollo glory days. We convinced ourselves that the path between the lunar dust and the Earth's surface was a paved road of settled science. We thought the thermal abyss was a dragon we had slain long ago. But the scorched, shattered underbelly of the Orion spacecraft has brutally redrawn the map of our reality. The space between worlds is not an empty, peaceful vacuum. It is a dormant ocean of kinetic energy, an invisible trap waiting to violently enforce the uncompromising laws of thermodynamics upon anyone arrogant enough to cross it. We are a species entirely defined by our defiance of boundaries. We engineer our way out of the cold, out of the dark, out of the fragile biological constraints of our own evolution. We write elegant equations that attempt to bind the chaotic infinite into neat, digestible variables running on silicon chips. But there is a profound, fatal arrogance in assuming that a mathematical model, no matter how advanced, can truly command the raw, vibrating fury of the physical cosmos. The spalling heat shield is the universe bluntly responding to that arrogance. It is a physical manifestation of a stark truth. Our mathematics are just shadows dancing on a cave wall. They are a desperate, flawed approximation of a reality that is fundamentally violent, fractal, and utterly indifferent to human survival. Consider the sheer terrifying fragility of our existence in the face of this cosmic architecture. We are temporary constructs of water and calcium, evolved to survive only within a microscopic, razor-thin layer of temperate gas at the absolute bottom of a planetary gravity well. To leave this sanctuary is to initiate a war against the absolute forces of nature. Every launch is a fleeting, desperate rebellion. Every successful return is a statistical anomaly. We wrap our astronauts in a few inches of synthetic resin, hurl them into the freezing void, and simply hope that the sacrificial burning death of that armor will be just enough to placate the thermal wrath of their return. We are not conquering space. We are merely surviving brief, agonizing trespasses into an environment that actively, mechanically seeks our eradication. The space agencies will press forward. The mission will not be abandoned. The engineers will tweak their algorithms. The technicians will adjust the composites, and eventually, the countdown clocks will resume. 4 human beings will climb into the apex of a colossal rocket, willingly strapping themselves to thousands of tons of explosive propellant. They will ride the fire into the dark, and they will inevitably face the harrowing, fractured mathematics of the descent. But the era of innocent exploration, the era of absolute engineering certainty, has burned away. When the sky eventually ignites above the Pacific Ocean, and the plasma sheath swallows the returning capsule in its blinding, deafening roar, we will not simply be watching the triumphant execution of human intellect. We will be watching a fragile, isolated species throwing itself blindly against the jagged walls of a thermodynamic quarantine, hoping against the cold, unfeeling machinery of the cosmos that the armor holds, and the fire lets them pass just one more time.